is I want to finish chapter 17 for the exam. So that's why I'm pushing it to the 25th. I will be replacing your lowest test grade with your final grade if you do better. But remember, this can only help you if you've done badly on one test. If you do badly on 2 tests, this won't do you any good. And also if you figure out what you did wrong, because the final is cumulative. So if you don't do better on the final, it's not going to help. I will not replace a test grade with your final grade if your final grade is lower. Your final already is worth a good bit of your grades. Keep that in mind. So we're going to finish up chapter 14. There's not much, because we won't really talk about thiols and sulfides too much. There's just a little bit I want you to be aware of. So thiols is a strong nucleophile, but remember they're not that great of a base as when we have the negative charge on the sulfur. And we'll look at that in a second. So because S negative is not a very good base, this is one of the few times where SN2 is going to be promoted over E2 because it's not a very strong base, but it's a very good nucleophile. So if we look at these examples, here, remember sodium is just our counter ion, so this is our thiolate ion, which is our sulfur with a negative charge. So a primary, of course, would just be an SN2 reaction, which is our normal SN2 reaction, forming a carbon-sulfur bond. And in the second example, this is still an SN2 reaction, but of course, this one has stereochemistry, so we would expect the inversion. No different than any normal SN2 reaction we've talked about. The only difference here when we're comparing this to O negative is, remember, O negative will typically promote E2 for secondary and tertiary. But thiols, we don't have that problem. The reason why thiols aren't very good bases when they have a negative charge is because of the equilibrium. If we look at reacting our thiol with hydroxide, and we look at equilibrium, what we're comparing is O negative versus S negative. And remember, when we're looking at the difference in size, the bigger the atom, the more stable the negative charge. So the equilibrium lies on the side of the thiolate ion, which is why it doesn't act as a base very well, because it stabilizes its negative charge with the size. It can still act as a nucleophile very easily, though. But as a base, it's not as reactive. So we see that our thiols have a much more acidic hydrogen than our alcohols. Again, these are all still weak acids, but it's stronger if we're comparing it based on our alcohol. So we see that with reactivity with our thiols. So they're strong nucleophiles, thiolates, that's our sulfur with a negative charge, but not great bases. It doesn't mean they can't be a base, they're just not great bases. They're not strong bases. One common bond that's going to be really important in biochemistry, so I'm not going to touch on it too much right now, is the thiolate forms, it can attack another thiol and form a disulfide bond. So this is a little bit different than other reactions we've seen. We won't see this really with an oxygen, but we can see this with a thiol. So let's say we have a strong hydroxide, so we can form a thiolate. If we put Br2 in there, our thiol can attack the bromine. Remember, Br2 is polarizable, and Br minus is a good leaving group. So we formed a compound that has a sulfur-bromine bond. We won't really see this with other functional groups. The alcohol doesn't really do this. And a second thiolate can come in and push off that bromine to form a disulfide bond. Disulfide bonds are found in nature. They're very important to biochemistry. And we see them a lot with things like protein folding and things like that in biochemistry. So they're very important. Our disulfide bond can easily be reduced. Here we're talking about reduction of the sulfur. Often in organic chemistry we're talking about the carbons, but in this case we're talking about reducing the sulfur bond back to a thiol. Usually with HCl and zinc, but we can use other materials as well. In the case of HCl and zinc, what happens is typically a homolytic cleavage to form sulfur radicals. And then remember, zinc it's a metal, so it can give up its electrons to form the thiolate. And then a little bit of acid will protonate it. Of course, this is a very reversible reaction. the sulfur-sulfur bond has a very low bond association energy, so we can easily form sulfur radicals. Bond association is about 53. So we see these types of reactions, again, very important biochemistry-wise. If you've ever gotten your hair permed, what you're doing is you're breaking the disulfide bonds in your hair, and then you wrap it around or you straighten it, and when you allow the disulfide bonds to reform, it allows your hair to be in a different texture. So really kind of interesting. Also why it smells really bad. You're breaking those disulfide bonds. So you're using harsh chemicals, but also the formation of the salt, the thiol, is not pleasant typically. So the next reaction we're going to talk about is oxidation of the sulfur. And this is a little bit more applicable to what we've been doing. So a couple of reactions of our sulfur analogs. One is an analog of an ether is called a sulfide, or a thioether. So what we see here, here's our ether. If this is a sulfur instead of an oxygen, it's a sulfide. Or you might hear thioether sometimes. So naming is very similar. If you're naming based on the really small sulfides, we have diethyl ether, this would just be a diethyl sulfide. So very straightforward as far as naming is that's concerned. If it's a side group instead of an alkoxy group like we have with the ethers, like propoxy or alkoxy, this would be an alkylthiol. So that's how we would name it as a side group. You do need to know these namings. I won't be able to actually run a test all the different namings, but you do need to know them. So here we have a methyl group, so this is a methoxy group if it was an ether. If it's a thiol, it's a methylthiol group. And oftentimes it's put in parentheses because it ends in an O, but I'm not going to be very strict with that. Sometimes it's just weird things with the naming. But methylthio, that means that's your sulfide functional group. And again, this one would be much easier to name based on this method because it's just not simple enough to name based on this method. So naming's very straightforward. So sulfides are generally prepared very similarly as we would prepare an ether, like Wittenson ether synthesis. But because of the acidity of our thiol versus our alcohol, we don't need the sodium hydride. Hydroxide's fine enough because remember that equilibrium would be forward because our SH is more acidic than H2O. And then we just need an alkyl halide. And the nice thing about this particular reaction here is that this can actually happen with a secondary alkyl halide because, again, E2 isn't really promoted because our thiol isn't a very strong base. So because our thiolate isn't a very strong base, we don't have to worry about that competing E2 reaction. Tertiary still doesn't work that well because SN2 still doesn't work well for a tertiary alkyl halide, just like we've been talking about since last semester. So it's still, we can do this with secondary. Remember, with the Wittenson ether synthesis, because the OH negative is a very strong base, we can't do that with a secondary alkyl halide. It has to be primary. But with the thiol, we actually can. Bless you. Now, technically, you can do this reaction with sodium hydride. Just you really don't need to waste your time working with such a reactive reagent because hydroxide is good enough with the thiol because of equilibrium. So sulfides can undergo a number of reactions. They can do an alkyl halide attack because we still have a lone pair, so it's still pretty nucleophilic even though we don't have a negative charge. And we form an S positive here. This is a really, really strong alkylating agent. So if we make this, we can then react it with another nucleophile, which would attack our carbon and make our SR2 a good leaving group. reforming our thiol. So this is a really nice way to put an alkyl group to a nucleophile. It's just very reactive, making a really nice leading group. So this is used in synthesis a decent amount. So once you form that 3, now of course you have to consider these R groups and what's the most likely carbon to be attacked. That can be an issue. If it's all the same, say it's all CH3s, then you don't have a problem. But if it's different R groups, then usually your attack will happen at the least substituted carbon because of sterics. So that is an issue with this particular reaction. You can have problems with that. But overall, it's a really nice way to make our carbon a very good electrophile. So this partial positive is pretty strong, and this is a great leader. So we have a good electrophile there. The other reactions we can do is we can do oxidation. And depending on which reagents, makes a difference on what our products are. So if we take our sulfide and we react it with an oxidizing agent, we can make the sulfoxide. You might notice something about this compound. It actually has 10 electrons around the sulfur, but sulfur can have an expanded octet because of where it is on the periodic table. We can further oxidize this to the sulfone here. To stop at the sulfoxide, there's a couple of reagents, but the one you need to know is sodium metapyridate, NaIO4. NaIO4 will stop at the sulfoxide. You don't need to know any other reagent, but you do need to know that one. So here we have this example, and we would stop here. We can use our stronger oxidizing agents, but it's going to go all the way to the sulfone. So for example, peroxide will react all the way to sulfone, as well as other oxidizing agents we've discussed, like our chromic acid. So we have to be careful. So the only one that you need to know is in the sodium IO4. That one will stop at the sulfoxide. Why is this typically used? Well, first, to understand these compounds, our sulfoxides and sulfones, even though we drew them with double bonds here, they actually don't have a lot of double bond character based on the resonance contributors. So here are 2 compounds, our sulfoxide and our sulfone. We typically draw them this way, but our most stable resonance contributor is actually the one with the charges. And this one actually has a 2+ charge and 2- charges. But typically we don't say our most stable resonance structure has charge. In these cases it does, because in both cases the charged compound has an octet instead of an expanded octet. So remember, having an octet will typically win when we're talking about our contributor. Though you often see them thrown this way in the neutral form. So there we have 10 electrons. In this case we even have 12. So again, sulfur can have an expanded octet based on where it is in the periodic table. But what we see here is this is our major contributor. Another thing to think about also is we don't have very good overlap between the orbitals of our sulfur and our oxygens, because sulfur is twice as big as oxygen. So those p orbitals and the pi bonds, the sulfur p orbital is much bigger than the oxygen p orbital. So instead of a normal overlap like a carbon-oxygen double bond overlap or a carbon-carbon double bond overlap, what we actually see is an overlap that looks more like this, because our sulfur is so much bigger. So we don't have as good of a pi bond overlap, so that also contributes to the fact that we don't have as much double bond character in that S oxygen bond. Because remember, the better overlap, the better the bond. And sulfur is twice as big. So that's also an issue. We have a 3p orbital versus a 2p orbital. We don't have that because the difference in size between carbon and oxygen is not very much. And the difference in size between carbon and carbon is 0. So here we don't have as good of an overlap. So like I said, these are used in common reagents a lot. Not so much, we're not usually trying in synthesis to make a sulfoxide or to make a sulfone. It's more the fact that our sulfides can be readily oxidized that makes them very good reducing agents. So for example, we've looked at ozonolysis, and we've talked about the fact that once we react O3, we'll usually throw in DMS. DMS is this, dimethyl sulfoxide. That's all the DMS stands for, dimethyl sulfoxide. The reason why DMS is used is because once we form this 5-membered ring structure, we need to reduce our carbon-oxygen double bond. And if we look at the carbon here, this is a reduction if you calculate the oxidation states between this carbon and this carbon. So that means that we can use the DMS because it oxidizes so easily to form DMSO and form our final compounds. So we hadn't really looked at that, what the DMS was used for before, we just said we threw it in. This is usually where our sulfoxides come in use, typically in reagents as a reducing agent in our compound. So now you know why we use DMS there. So if we look at this example, if we take this salt, this thiol, we react it with sodium hydroxide, we will deprotonate it, and then it will attack our partial positive carbon of our alkyl halide. Now remember, this is an SN2 reaction, so we're going to get inversion of stereochemistry. So there is our inversion of stereochemistry that we see at that partial positive carbon. Then we have a oxidizing agent, NaIO4. This one will stop at the sulfoxide, so we draw that one. If we want to go all the way to twice the oxidation, then we would use peroxide, or a stronger oxidizing agent. So looking at this one, there's a very similar reaction. We're deprotonating, we're reacting it with this partial positive carbon. And then excess H2O2 means we will oxidize it fully, which would give us A. Now we're not inserting an oxygen in anywhere. That's not happening. And this is our intermediate before the oxidation. That's our intermediate compound. And of course that carbon is not a stereocenter, so where the SN2 reaction happens, there's no change in stereocenters because it's not a stereocenter. So that's all of chapter 14. Now we're getting into chapter 17. Chapter 17 is looking at conjugated pi systems, and then pericyclic reactions, which hopefully we get to, but we're definitely going to get through the conjugated pi systems. So first thing we're going to do is define what conjugated means. So there's 3 categories of dienes, which are compounds that contain 2 double bonds. One is cumulated. That's where our pi bonds are adjacent. Oftentimes you hear these defined as allenes. Now remember, you don't have any resonance here because one pi bond is in one plane and the other pi bond is in the other, because we can't have 2 unhybridized p orbitals in the same plane of one carbon. These are not very stable. We won't look at these very much. We don't have much overlap, so these are very specific compounds and won't typically form easily. The next example is conjugated, and this is where each double bond is separated by one single bond. And what happens is we have overlapping p orbitals, completely overlapping p orbitals, so that means those electrons and those pi bonds are shared between all of the overlapping p orbitals. That's our conjugated systems, and we see very specific types of reactivities based on these conjugated p orbitals. The last one would be isolated, where you have at least one sp3 carbon between your pi bonds. You no longer have that overlap because there's an sp3 carbon with no p orbital. So the electrons in the pi bonds are isolated to their bond. They're not being shared between multiple p orbitals. And in this class, this particular chapter, we're going to be focusing on our conjugated double bonds. So only a continuous system of overlapping p orbitals. We're going to be describing a lot of what we're seeing based on the p orbitals, because a lot of the reactivity is going to be coming from the pi electrons. So we don't really care, or we're not really going to be discussing too much the electrons in the sigma bonds, only the electrons in the pi bonds. Remember, there's 2 electrons in every pi bond. So that's what we're going to be looking at, and we're going to specifically be looking at those electrons. Heteroatoms may also be involved in the conjugated system, so it doesn't have to be just a carbon-carbon double bond. It could be a carbon-oxygen double bond as well. That still has 4 p orbitals that are overlapping with no sp3 carbons blocking that. So that's still conjugated. Here is another conjugated system where this double bond, even though there's a nitrogen there, is participating in conjugation with this ring. Now this pi bond is isolated because there's an sp3 carbon and an sp3 carbon. So we don't have conjugation with that double bond. So what we see is this. And you can see those isolations right here. We don't have p orbitals there. Conjugated systems are very important for electronics. We use a lot of conjugated systems for electronics, where we have these overlapping p orbitals, so electrons can be transferred throughout the molecules, and therefore we use them in electronics. So a lot of conjugated polymers are used for electronic devices based on these conjugations. Because again, what is just electricity? It's the transfer of electrons. So when we have these p orbitals that are in conjugation, they can transfer electrons. So looking at these systems, we can look at conjugation. So all of these double bonds are in conjugation, and in fact the lone pairs on this oxygen is also in conjugation. We can draw resonance structures with those. Because remember that lone pair can be in an unhybridized p orbital if it allows for resonance. So those are all conjugated, but this double bond is isolated from the other double bonds. Same thing here. We have this isolated system because we have the sp3 carbons in between, but these 2 pi bonds are in conjugation. And even though they're not between a carbon-carbon double bond. So of course, this is a conjugated system. And how many pi electrons do we have in this conjugated system? 10. We have 10 electrons in the p orbitals. Remember, there's 2 electrons for every pi bond, and there's 5 pi bonds. So there are 10 electrons that are all participating in those p orbitals. How many p orbitals are there? Unhybridized p orbitals. How many p orbitals are there on each carbon of the double bond? There's 10 unhybridized p orbitals. Each carbon has an unhybridized p orbital that is in the pi system. Remember, we cannot have a pi bond without an unhybridized p orbital. That carbon doesn't have an unhybridized p orbital because it is sp3. But all of our other carbons in this system are sp2. So we have 10 pi electrons and we have 10 unhybridized p orbitals in conjugation. And that's going to be important for what we're going to be talking about in the next couple of slides. I don't know why it does that. So first we're going to talk about how to prepare them. And you should be able to name them because remember, it's just based on how many enes we have. So to prepare them, what we can use is a sterically hindered base to form our dienes. And that avoids competing substitution reactions. So let's say we have a double bond. Then we're going to form the conjugated diene. We like to use that bulky base just so we don't have any substitution occur. This is our most stable double bond to form. it's really unlikely that we would form the cumulated double bond by deprotonating this position, because electrons in conjugation are much more stable. So we're going to form our more stable product. If we have two leaving groups and a bulky base, we can again form the same compound. So either we need a double bond present and an adjacent leaving group, or we could have two adjacent leaving groups and form our diene. And this is just elimination reactions. So let's talk a little bit about our bond lengths. If you recall, a carbon-carbon single bond is about 153 picometers, but the carbon-carbon single bond between our two double bonds is actually a little bit shorter. There's a couple of things we can use to explain that difference. One is the hybridization of the carbons. Remember, these two carbons are sp2, and that means that all of our orbitals that are hybridized are sp2. And our sp2 orbitals are shorter than our sp3 orbitals. So we have more s character. Our p orbital looks like this. Our sp3 is a little bit shorter because we're mixing one s and 3p orbitals. sp2 is even shorter because we're mixing one s and 2 p's because the third p is unhybridized. And then, of course, our triple bonds are the shortest. So because of that, remember our sigma bonds or a head-on overlap. So because we have a bond between two sp2 hybridized orbitals, then it's a bit shorter than our sp3. So that's one explanation for why that bond is shorter. We're going to be looking at another explanation soon. As far as stability, we can often compare it to stability by looking at our hydrogenation. So that's just our reduction reaction from a double bond to a single bond. Now, having a pi bond is always going to be more unstable. But if we're comparing our double bonds, typically what we see is conjugation gives us a little bit more stability. Still not as stable as a system with no pi bonds. So double bonds do increase in stability. But if we would compare our diene that's conjugated with our isolated diene, we'd see it to be more stable. If we were comparing our diene with the accumulated diene, the accumulated would be even less stable because, again, we don't have any overlap. So having that conjugation, the fact that those, in this case, 4 pi electrons, there's 2 pi electrons here and 2 here, are in conjugation and shared between all 4 of those unhybridized p orbitals, gives it stability. Now still, the more p orbitals, typically the more pi bonds, the more unstable. Now that's not quite the same discussion for a carbon-oxygen pi bond. Those are more stable because they have a resonance structure. So this is when we're going to talk about carbon-carbon double bonds. So the more conjugation of our double bond, the more stable. But in general, the more pi bonds, the less stable the entire molecule. So looking at these and putting these in order of increasing stability. Here, so what we have is A only has 2 pi bonds, B has 3, C has 3, and D has 3. So A is going to be our most stable, no matter the conjugation, because we have less pi bonds. So that's typically what we see. So here's our pi bonds in red. So A is our most stable. Then, if we're comparing the rest, we see D is all in conjugation. And we have 2, 4, 6 pi electrons, and 1, 2, 3, 4, 5, 6 unhybridized p orbitals. Remember, all the other carbons do not have unhybridized p orbitals. So D has the most conjugation, so it's the next most stable. And remember, these are trigonoplanar, so all these pi bonds are flat on the page. C and B both have about the same amount of conjugation. We have 2 pi bonds in conjugation in both C and B. So the question is, which one's more stable, C or B? Well, we have the same amount of conjugation, so now we can look further at what we typically look at for pi bond stability. And remember, the more substituted pi bond, the more stable. So we've seen that a lot. So what we see as B and C are both have the same degree of conjugation. So they're both looking at stability, not as stable, but if we look here, we have a quadri-substituted, a tri-substituted, and a di-substituted, versus here we have a di, and a tri. So this one, especially this one, has the most substitution, so B is a little bit more stable than C. So once you look at conjugation, then you're just comparing what we compared after for our stability, which is substitution. Remember, our more substituted pi bonds are more stable. I wouldn't ask you to say, tell me how much more stable A is over B, but you should be able to put them in order. In general, our single bonds between our pi bonds can freely rotate, so we still see this. Now the barrier of rotation is a little bit higher, because when you rotate, you lose conjugation, but we can still have rotation, especially at room temperature. If we were to cool this down, we'd see a less amount of rotation at lower temperatures, but at normal room temperature and a little bit higher, we see free rotation. So there's two ways we describe the pi bonds. We can have the S-cis conformation. Now remember, this isn't really a cis. The S-cis just means that it's like a cis, because our pi bonds are on the same side, versus the S-trans. This is going to be really important for some of the reactions we're going to be talking about in this chapter. So S-cis just stands for single bond between the two double bonds. S-cis is cis-like, has a dihedral angle of 0 if we were to draw this in Newton projections. And then our S-trans is like trans, where our dihedral angle is 180. The S-trans is a little bit more stable because, again, sterics, just like our normal trans is more stable because of sterics. But remember, the difference here is you cannot have a rotation between a cis and a trans double bond. You would actually have to break the double bond to move from cis and trans. But we do have free rotation, so this is just the terminology. At any given time, unless if something else is keeping the double bond in the S-cis conformation, we typically have it in the S-trans. An example of that would be if we had this diene in a 5-membered ring. This is kept in the S-cis conformation, but clearly we don't have free rotation here because it's in a ring. But typically, if we do have free rotation in other examples, then it's kept in S-trans for most cases. Other possible conformations during the rotation is going to have our pi bonds not be in conjugation. Notice they're still in conjugation in both of these examples. But when we rotate, the process of rotating will put it out of conjugation. So what we see is we have a higher barrier of activation than a normal carbon-carbon single bond. A normal carbon-carbon single bond, that barrier of rotation is like 2 kilocals per mole. This one's a lot higher. But under normal room temperature, we can have this occur. So about 98% of the molecules are in that S-trans form. But as you can see, this barrier comes from the fact that we don't have conjugation. And the conjugation is what makes our conjugated pi bonds more stable. So the p orbitals are not overlapping while it's rotating. This is going to bring us to a concept of molecular orbital theory, and we're going to be using this throughout this chapter, so I'm going to spend some time with it today. So molecular orbital theory, we've looked at slightly in organic one, but it's really, really useful for these conjugated systems. So let's do a little bit of review there. A molecular orbital forms when atomic orbitals overlap. Our atomic orbitals, if we're looking at the bond between our two carbons here for this pi bond, our atomic orbitals are an unhybridized p orbital on each carbon. So each carbon has an unhybridized p orbital. So that's our atomic orbitals. We have 2. Those 2 p orbitals can either overlap the same phase. We'll either, when we draw our unhybridized p orbitals, remember this is just showing the positive or negative answer to a big equation, not a charge. So we'll often show it as red or blue, but when you're drawing it, what we'll typically draw is shaded and unshaded. And a good overlap, a constructive overlap, is where the blue and the blue overlap and the red overlap, or the shaded and the shaded overlap. When we have a overlap like this, then we don't have good overlap because this is destructive, so we have a node, which is a zero possibility of electrons being there. Anytime you have a node, that's higher in energy than not having a node. So our molecular orbitals are describing the entire molecule. Our atomic orbitals are describing just the atom's orbital. So here, if we're looking at the double bond overlap for just the pi bond, and this is also going to be key, that we can look at just the outermost orbital. We don't have to look at the sigma bond for these because they're lower in energy, so they're not going to be participating in the reactions that we'll be talking about. So we're not even going to map them out. We're only going to map out the outer layer where the reaction is going to occur. So the atomic orbital is just our unhybridized p orbitals, and then they come together to form our pi bond. So our molecular orbital does extend the entire molecule. Bonding is going to be more stable than anti-bonding. Bonding is when we have constructive overlap. Anti-bonding is when we have destructive overlap, and here we have a node. So notice that anti-bonding has a node that's a place of zero energy that electrons can be. Remember, this is all probability and based on a big mathematical equation that we're not going to have to know, but we just have to be able to map this out. So because the electron cannot be there, remember our electrons want more space. The less space we give an electron, the less stable, so the higher in energy. So that's what we're mapping out. So what this shows is the p orbital of one carbon and the p orbital of the other. And they each have an electron, so they're coming together to form a pi bond, and our bonding orbital has those two p orbitals overlapping, and then our anti-bonding doesn't. So that one's higher in energy, but our bonding is lower in energy than our starting p orbitals, because now we have two electrons instead of one unpaired in each. That's not very stable. So for reactions, our two most important orbitals are going to be our HOMO, which is our highest occupied molecular orbital, and our LUMO, which is our lowest unoccupied molecular orbital. If our pi bond is acting as a base or a nucleophile that's giving up its electrons, which orbital is those electrons going to come from? The HOMO. So that's why it's our most important orbital, because that is our outermost electrons and our most accessible. Now, if the pi bond was accepting electrons, where would they go? The LUMO, because this is our lowest energy orbital that is empty. So in any molecular orbital diagram, our most important molecular orbitals are going to be our HOMO and our LUMO. Remember, when we're filling in electrons, we fill the lowest energy first and pair before we go up. If we have degenerate orbitals, we pair across before we start pairing. But in these conjugated systems, we won't ever have degenerate orbitals. We're always going to have only one orbital in the higher energy and higher energy. So we're going to look at that. So you're going to have to draw your molecular orbital diagrams for your conjugated pi systems. So molecular orbital theory says that a general characteristics for a linear combination of orbital systems. This is just saying, we just looked at one pi bond. But what if we have multiple pi bonds in a row that are conjugated? So we can look at some general combinations of this particular math product. First, the number of atomic orbitals is going to equal to our number of molecular orbitals. For this example, we started with two unhybridized p orbitals, so we formed two molecular orbitals. So that's going to be key. If we start with 4 unhybridized p orbitals, we're going to have 4 molecular orbitals. If we start with 16 unhybridized p orbitals, don't worry, I won't ever have you draw 16, that would take too long. You would have 16 molecular orbitals. So however many unhybridized p orbitals in our system, that's how many molecular orbitals you're going to be drawing. As your number of nodes increases, the energy of the orbitals increase because you're giving your electrons less space to be shared. The total number of interactions defines whether your molecular orbital is bonding, non-bonding, or anti-bonding. So bonding just means we have more positive interactions than negative. And by positive and negative, this is positive, this like interaction, and this is negative. So with our 2p orbitals, we only have completely bonding and completely anti-bonding. But when we're going to have multiple p orbitals, we'll have some cases where some of the p orbitals will be bonding and then some will be anti-bonding. So our overall bonding is going to be more positive. Our overall anti-bonding is more negative than positive. Those are going to be higher energy. And we won't really see any of that in this particular chapter, but in the chapter where we start talking about aromaticity, we'll see some of this. Non-bonding is where you have an equal amount of good and bad interactions. But because of the systems we'll be looking at in this particular chapter, we won't really see too much non-bonding. The other thing, we're going to be drawing these representations. Because it's a math problem, then molecular orbitals are only ever going to be totally symmetric or totally anti-symmetric. Because again, this is a math problem. So this is really a pictorial representation of what this big equation would give us. So it can't be asymmetric because of that. So what do I mean by that? Here, these blues are equal to each other, so we have symmetry. Here, it's still symmetric, but it's completely asymmetric. It's not non-symmetric. So if we were to rotate, then the red would be here and the blue would be here. And then rotate again, that would be opposite. And this is also symmetric. What wouldn't be symmetric, what would be an example of not being symmetric would be an example like this. This one's not symmetric or anti-symmetric because our node is here and we only have one p orbital and 3 on this side. So our nodes are always going to have either complete asymmetry or complete symmetry. So we won't have something like this. And again, it has to do with the fact that this is a math equation. And lastly, our highest energy atomic orbitals lead to our highest energy molecular orbitals. So what that means is the most important are our HOMO and LUMO. Those are going to be our outermost energy electrons. All this means is that we do not have to look at our sigma bonds. They're inner, so our HOMO and LUMO will never be part of the sigma bond system. It's only ever going to be part of the pi bond system. So we're only going to be looking at our unhybridized p orbitals. We do not care, at least for these discussions of our molecular orbital theory, about our sigma bonds. We're not mapping out our sigma bonds. They would be lower in energy, so those electrons are not accessible until we break the pi bond. So because of that, we're not even going to look at them. And that doesn't mean we couldn't draw them. It would just be a waste of time because we can approximate what we need by only looking at our unhybridized p orbitals. So we won't be looking at the sigma bonds or the electrons in the sigma bonds. We're only going to be looking at our pi electrons. So the electrons in the pi bond. So let's look at this simple one. We've looked at it a little bit. Here we have our ethylene. So we just have our pi bond. We have 2 unhybridized p orbitals, so that's all we're going to map out. So that means we'll have 2 orbitals. So here's our 2 unhybridized p orbitals, our 2 atomic orbitals. So we're going to have 2 molecular orbitals. We're going to have completely, in this case, symmetric and completely asymmetric. So we have only bonding and anti-bonding. Oftentimes you'll see the HOMO and the LUMO as pi and pi star. But you don't necessarily have to label them like that, but you often see it. Now remember, that means we're starting with 2 pi electrons. So we're going to fill the lowest level first before we go up. And we always pair before we go up in level. This you learned from general chemistry. So that's nothing new. So our bonding electrons can freely move between both of the orbitals. But if we had any electrons in this pi star, then we wouldn't have free movement, which is why this is higher energy. Now, under like conditions, we can excite an electron to this, but it'll relax back down really quickly. We'll be looking at that for some reactions as well in this chapter. So that's where that star comes from. That is our lowest unoccupied molecular orbital. So this is in phase for our bonding. And for our anti-bonding, notice we don't have this overlap. So the electrons cannot be shared between them. So let's look at this one. This one's a little bit more complicated because here we have 4 unhybridized p orbitals. So we have butadiene, and again, we do have this sigma bond, but we are not mapping it out. We're only mapping out our outermost orbitals, which is our p orbitals. So we have 4 unhybridized p orbitals. So that means we have 4 atomic orbitals. How many molecular orbitals are we going to have? 4. The amount of atomic orbitals we have is the amount of molecular orbitals we're going to have. We have 4 p orbitals, so 4 molecular orbitals. So here's our 4 p orbitals. Your lowest energy is going to be all of your p orbitals completely bonded. So when you're drawing this, and you will be drawing these, you would shade, and it doesn't matter if you shade all the top or shade all the bottom, as long as you're consistent. I always shade at the top, but it's kind of irrelevant. The shading versus a non-shading is just representing that we're above the plane of 0 versus below the plane of 0, because our electrons act as waves. So that's all that means, either above or below. It's irrelevant. But what is relevant is you would draw it like this, all shaded together. Here it's showing pink and red, pink and blue, but you don't have to use colors if you don't want. Then our next one will have 1 node. So remember, we have to have symmetry. So for symmetry, that node would go straight in between. We still have some bonding, and we have 1 anti-bonding. So we still have mostly bonding overall. This would be a bonding orbital. This would be a bonding orbital because we have more good interactions than bad. This is good, this is good, this is bad. So we have 2 good and 1 bad. And again, our node is in the middle, so we have that asymmetry. The next one, of course, will have 2 nodes. Again, notice that symmetry. This is the only place I can put those nodes and still have symmetry. If I put a node here, then I have 2, 1, and 1. That's not symmetric. So this one would be getting into anti-bonding, because now we have 1 good interaction and 2 bad interactions. Bad interactions is those nodes. Blue does not overlap with red. But red and red overlap, so that's a good interaction, and then red does not overlap with blue. So we have 1 good interaction but 2 bad, so this is anti-bonding. Lastly, our 4th one, the bottom one and the top one are the easiest, because our 4th one would be completely anti-bonding. So when you're drawing these, whether I give you 2 pi bonds or 3 pi bonds or 4 pi bonds, your lowest is always going to be completely bonding. Your highest energy is going to be completely anti-bonding. So notice, because we have 4 p orbitals, we can have a maximum of 3 nodes, a node separating each of those p orbitals. So your nodes are always going to be 0, 1, 2, 3 until your top one. You always have an increase in 1 node. The last step in drawing this full orbital diagram is putting in our electrons. So we have 4 pi electrons. Again, we're only mapping out the electrons in the p bonds, the pi bonds. We don't care about the inner electrons. So we have 4 total electrons in that conjugated system. So we're going to plug those in. We start at the bottom, pair it before we go up, and then there you go. So this is our HOMO as our highest occupied molecular orbital, highest in energy, so what we mean by highest. And this is our LUMO. And we'll be really using that to explain our reactions in this chapter. So this would be your full molecular orbital diagram. Now you don't need to draw this is just to help you visualize it, but if I ask you to draw a molecular orbital diagram, I do want these p orbitals drawn. I want these. This psi is just your eigenfunction. You don't necessarily need to, but often it's labeled as psi 1, psi 2, psi 3, and psi 4. If you had 6 unhybridized p orbitals, you'd have 6 of these. Again, your lowest would be completely bonding, your highest would be completely anti-bonding. So this is another way we can explain the energy of that single bond between our double bonds. Also, this helps us to explain our conjugation. If we look at our conjugated system, versus an isolated system, we don't have the same type of orbitals because of this sp3 carbon in between. We're never going to have a good interaction between these because we have no interaction between those because we have that carbon that's blocking the conjugation. So what we end up with is degenerate orbitals, and what that means is we have an extra good interaction in our conjugated system, whereas we have no interaction with our system here. And notice these two are in the same energy. And the reason why is they have the same amount of good and bad interactions. This has two good interactions, this has two good interactions, so the same level. This is completely anti-bonding, so at the same level. That's why we have degeneracy. We'll never have degeneracy in our conjugated systems. So the result is our energy gap between our HOMO and LUMO is smaller for our conjugated system, and it's bigger for this system. So that means electrons have more place to move around in our conjugated system, so it makes them more stable. The last thing I wanted to show you was a little bit of practical stuff. So conjugated systems also affect where we can see them. Remember, when we're looking at spectroscopy, lower wavelength means higher frequency. So we have higher energy that way. Lower energy is this way because it's a higher wavelength. So lower frequency, so lower energy. If we look at just a double bond, our band gap is about 175 nanometers. With spectroscopy, we could, light will come in, it will excite one of these electrons. If light comes in at this exact amount of nanometers, excite this electron, it will fall back down, we'll see a photon. So that's where the light comes from. But once we have more conjugation, that gap gets smaller. So since that gap gets smaller, what we see is a different wavelength. So conjugated systems, we can typically see them under UV light. The more conjugated system, again, we can only promote an electron to the excited state at the exact amount of energy. So we see that getting over. The more conjugation, the smaller the energy gap. We look at something like beta carotene, we actually see it in visible light. What is beta carotene from? Carrots. If it's being absorbed by blue light, what do we see? Orange. That's why carrots are orange, because of beta carotene. It's orange because of these conjugated systems and an energy gap being small enough to where we can actually see it in visible light. So application-wise, we can use organic chemistry to explain what we see with this type of molecule. So that's where I'm going to stop today. And we are going to continue with this on Wednesday. Don't forget, fall break is Thursday and Friday. Yay. So we will not have a review on Wednesday like I had originally said. It will be sometime next week, so I'll be posting that.